Good afternoon. Anybody has joined?
Good afternoon, sir. There are 6 students in class.
6 students. Okay. So today we'll discuss about the game theory. Yesterday the assignment problem we have discussed, and I have uploaded all the files in the MS Team. Have you seen that file? In MS Team, I have uploaded that the 10 ABC and 11 ABC. 3 different files for the transportation problem, 3 different files for the assignment problem. Yesterday I have uploaded.
Yes, sir.
Yes? Is there?
Yes, sir, it's there.
Okay. So actually this is the last topic. This is very similar to the linear programming. Generally, we solve the game theory problem by linear programming method. So we'll discuss, say, how do we formulate the linear programming problem for a game theory problem and how to solve. So we'll discuss about this. Mainly, and for the game theory, we'll discuss about the only 2-person zero-sum game. 2-person zero-sum game. Why 2-person? Because either 2 players are involved, or 2 persons are involved, or 2 different groups are involved. And we said it's zero-sum because whatever one party is gaining, same amount the other party is losing. So, and net loss and gain equal to 0. So zero-sum. So what one is gaining, that is coming from the other party, and similarly what one is losing, that is going from one party. So this is the game theory. So mainly any problem, any game 2-person zero-sum game theory problem, we can formulate in terms of a matrix game. So let us know about the game theory. So for example, as you know, life is full of conflict and competition. For example, the present war, maybe particular game. Mainly you are talking about the and there is the 2 groups, the game between 2 groups or player between 2 groups or 2 party. Real life examples involving adversaries in conflict include parlor games, military battles, political campaigns, advertising, and then marketing campaign by competing business firm and so forth. A basic feature in many of these situations is that the final outcome depends primarily upon the combination of strategy selected by the parties or the groups. Strategy. So mathematically, game theory is a mathematical theory that deals with general feature of competitive situation, like this in the formal abstract way, in places particularly emphasis on the decision making process of the adversaries. Research on game theory includes many complicated types of problems, competitive situation. However, in this game theory, we will talk about the 2-person zero-sum game. 2-person zero-sum game. 2-person zero-sum game. As the name implies, these games involves 2 players or 2 parties. They are called zero-sum game because one player wins whatever the other one loses, so that sum of their net winning is 0. Zero-sum game because one player wins whatever the other one loses, so that the sum of their net winning is 0. In general, a 2-person game characterized by the strategy of the player 1, strategy of the player 2, and the payoff table. So we are naming, let me say, player 1 is player A, player 2 is player B, and how do you define a payoff matrix? So in this game, we have presented a payoff matrix. So I will define what is called a payoff matrix. There are two different players, player A and player B. Player A and player B. Player A is the first player, player B is the second player. Generally, player A, the rows are for the player A. There are m number of rows. So these A1, A2, AM, these are nothing but the strategy. The player A select either strategy number 1, A1, or strategy number A2 or strategy number AM. There are m number of strategy for the player A. Similarly, the player B is selecting the columns. So B1 stands for the strategy 1 for the player B, B2 stands for strategy 2 for the player B, and similarly BN stands for strategy N for the player B. The player A has m number of strategy, that is m number of rows. Player B has n number of strategy, that is n number of columns. Now, how do you define the elements A11, A12, A1n, A21, etc.? How do you define? So, if player A selects his first strategy A1 and player B selects his first strategy B1, A11 is the payoff. This A11 is a real number. It can be positive, it can be negative, it can be 0. If it is 0, then A is not paying anything to B or B is not paying anything to A. If A11 is 0. If it is positive, let us say A11 equal to 10. If it is positive, then B1 paying 10 units to A1. If it is positive, B1 paying 10 units to A1. If it is negative, then A1 paying 10 units to B1. So how it is 0? See, if A1 paying to B1, whatever A1 is paying to B1, one is gaining and another is losing. Then loss and gain together equal to 0. If it is 0, there is no loss, no gain. Similarly, in general, so if the player A selects his ith strategy and player B selects his jth strategy, Aij, the element Aij is the payoff from B to A, if this is positive, if it is negative, then the payoff is from player A to player B. If it is 0, then there is no gain for anybody. Okay. These Aij elements, there are m into n number of elements due to this matrix. This matrix has m number of rows and n number of columns. So it has m into n number of elements. They are real numbers. So this matrix is known as a payoff matrix. Here A1, A2, AM are the strategy for the player A. Similarly, B1, B2, Bn are the strategy for the player B. Strategy, for example, I can say for a particular game. So the strategy, number of strategy for the player A and the player B may not be same. If two countries are going for some war, the number of strategy, whatever the weapon the one country has, other country may not have the same weapon. Okay, they are different. Okay, so different strategy for the different opponent. Two opponents are there. So similarly, B1, B2, Bn are the strategy of the player B. Now, if you are defining the payoff elements of the payoff matrix Aij, the real number Aij is the payoff to player A by B when the player A plays strategy AI and player B plays strategy Bj. If Aij is negative, B receives, otherwise A receives. If Aij is negative, then it is gain for B. If it is positive, then it is gain for A. So now we are talking about a payoff matrix. There are two players, player A and player B. Player A has two strategies, strategy 1 and 2. Okay. This player B has also two strategies, strategy 1 and strategy 2. So if player A selects his first strategy and player B selects his second strategy, that is, as you know, the outcome is 4. Who receives 4 units? The A receives 4 units. Okay. Now similarly, the player A selects his first strategy, player 2 receives his second strategy, then A receives 5 units. Here 4, then 5. If player A selects his second strategy and player B selects his first strategy, this is the payoff is 2 units, and both are using the second strategy, utilizing the second strategy, the payoff is 3 units. So here in this payoff matrix, all the elements are positive. It is a gain for A. It is a gain for A. But we are interested to know what is the value of the game. What is the value of the game? And what are the optimal strategy for the player A and player B? So that we want to know, but this is the payoff matrix only. This is a 2 by 2 matrix. Payoff matrix is a 2 by size 2 by 2 because A has 2 rows and B has 2 columns. A has 2 different strategy, A 1 and 2, and similarly B has 2 different strategy 1 and 2. So with respect to this, we have and we are naming. This is an example of a stable game. This is an example of a stable game. How do conclude it is a stable game? Stable we find in this manner. So there are 4 elements. So with respect to these 4 elements, the first row has 2 elements, 4 and 5. 4 and 5. So with respect to 4 and 5, we find the minimum equal to 4. And second row has 2 elements, 2 and 3. So minimum of 2 and 3 equal to 2. So first row minimum is 4. Second row minimum is 2. Again, minimum of these 2 elements, 4 and 2, maximum of 4 and 2 equal to 4. First take the row-wise minimum, then take the maximum. Similarly, take column-wise minimum, column-wise maximum. First we are taking 4 and 2 maximum is 4, and 5 and 3 maximum is 5. Then you take minimum is 4. So after taking the column-wise maximum, we are taking minimum. After taking the row-wise minimum, then you are taking maximum. This minimax and maximum both are becoming equal to 4 units. So we conclude that the game is stable. I'm repeating again. Row-wise take the minimum. First one is 4. Second one is 2. Then you take maximum. Maximum is becoming minimum. Then maximum. So maximum is becoming 4. Then column-wise you take maximum is 4. Then second column, maximum value is 5. Then you take minimum is 4. So that minimax and max mean. So minimax and max mean both are becoming equal. So we conclude that the game is stable. If game is stable, what is the value of the game? The value of the game equal to 4. This is 4, the value of the game. And what is the optimal strategy? Optimal strategy, player A is using his first strategy, player B is using his first strategy. The value of the game is becoming 4. A is trying to maximize his gain. B is trying to minimize his loss. A is trying to maximize his gain and B is trying to minimize his loss. As a result, this is the outcome. The value of the game equal to 4. 4 means it is a gain for the player A and optimal strategy, that is A1 and B1. Optimal strategy. This is an example of a stable game. Now, I am just citing another game, another 2x2 matrix game. So the elements, the A has 2 strategy, A1, A2. B has 2 strategy, B1, B2. Now the elements is given here in this manner. Elements are given here in this manner. 2, -3, -3, 4. First row elements 2, -3. Second row elements -3, 4. So this is the payoff matrix. And we are saying the game is unstable. What is the reason? So once you are saying game is unstable, we'll check again row wise. What is the minimum of first row elements? What is the minimum of the first row elements? What is the minimum? Please tell me.
-3.
-3. And what is the minimum of the second row elements?
-3.
-3. So what is the maximum then? Maximum is same. -3, -3. So maximum is -3, let us say. Now take column wise maximum. Column wise maximum. The first column 2 and -3. What is the maximum? 2. Second column -3 and 4. What is the maximum?
4.
4. Among these two maximum, take the minimum. This minimum is becoming 2 and 4. The minimum is 2. Minimum is 2. There got a maximum is -3. Okay. They are not equal. They are not equal. So the game is a unstable game. The game is unstable one. Now, how to find the value of the game? So here directly the value of the game we cannot compute. We can compute only expected value of the game. Expected value of the game. So what is the expected value of the game? Now, you know 2 strategy A1, A2. B has 2 strategy B1, B2. So since this is a unstable game, so pure strategy is not applicable. So we will apply mixed strategy. Mixed strategy means we will have some probability distribution. Probability. See, what is the chance of using first strategy? Say A has 2 strategy. Say chance of using first strategy, let me say P1, and chance of using second strategy is P2. And since there are 2 strategy, P1 plus P2 equal to 1. Similarly, the player B has 2 strategy, chance of using strategy 1, let me say it is Q1, and chance of using second strategy is Q2. Q1 plus Q2 equal to 1. Okay. Now with respect to P1 plus P2 equal to 1, and both are P1, P2 are non-negative, the probability, and Q1, Q2, they are also a probability, they are non-negative. Q1 plus Q2 equal to 1. So we are interested to know what is the expected value of the game? What is the expected value of the game? So this expected value of the game, so for the unstable game, we are interested to find the expected value of the game. Can you guess anything? What is the expected value of the game? Anybody can guess?
So it will be the sum of the product of the probability and the payoff corresponding to that, right?
It's not like that. So we have some methods. So we have learned how to solve a stable game. The unstable games, there are some methods we will learn very soon to solve the problem. Okay. So I will not let me say. So if I'm talking about say half, probability of using first strategy equal to half, second strategy also half, P1 plus P2 equal to 1. P1, P2 are equal. Similarly, Q1, Q2, okay, they are also equal, half. So what will happen? The expected value. What will happen? The expected value. Row wise, you can see 2 plus 3, 2 plus minus 3. So that is coming minus half. Here also coming plus half. Okay, they are not equal. Okay, so similarly, this is we have to know what is the value of the. So this one half may not be the solution, but I am just guessing whether half is the solution or not. So we can solve it. Okay, this is an example of an unstable game. So I am not giving any answer to this problem. Okay. Primarily, objective of the game theory is the development of rational criteria for selecting a strategy. Two key assumptions are made. Both players are rational. Both players choose their strategy solely to promote their own welfare. Okay, so this is our assumption, and optimal solution of two-person zero-sum game. Problem 1, let us say, determine the saddle point of the solution. Saddle point means this first example. This is a stable game. So the 4 is this saddle point. These saddle points give the value of the game. Okay, so the first problem. So now problem 1 said determine the saddle point solution, the associated pure strategy and the value of the game for the following problem. See here, I have considered a bigger size problem. So this player A has how many strategy? The player A has how many strategy? 3 strategy, A1, A2, A3. Player B has 4 strategy, B1, B2, B3, B4. Generally, we are naming player 1 and player 2. And player 1 is nothing but the player A. Player 2 is player B. Player 1 selects only the rows. Player B selects the column, row and column. And you can interchange also. So if you interchange, then the other way, we can say in place of A, B will come. In place of B, A will come. But generally, this is the rule. So rows for the first player and columns for the second player. Rows for the first player and column for the second player. Now, you can see here, these elements, these first row elements, 8, 6, 2, 8. So now somebody may ask question, from where you got these elements? From where? So already a problem has been formulated. This is the payoff matrix. From the payoff matrix, we like to take decision. From the payoff matrix, we like to take decision. Okay. So in some problem, we'll also formulate our payoff matrix. So here in this problem, the first row, there are 4 elements, 8, 6, 2, 8. 8, 6, 2, 8. What is the row wise minimum? Minimum is 2. Second row has 4 elements, 8, 9, 4, 5. What is the row wise minimum? Row wise minimum, that is also here. First row has minimum is 2, second row minimum is 4, and third row 7, 5, 3, 5, and minimum is 3. So with respect to 2, 4, 3, what is the maximum? Row minimum, then we are finding maximum. So that is known as max mean. First take the minimum, then maximize, max mean. Okay, max mean, the max mean 2, 4, 3. What is the max mean value? What is the max mean value? Maximum value is 4 units. Yes or no? Hello?
Yes, sir.
Similarly, now take column wise maximum. First column 8, 7, 8, 8, 7. So maximum is 8. Second column 6, 9, 5. What is the maximum? Maximum is 9. Third column 2, 4, 3. Maximum is 4. Fourth column 8, 5, 5. Maximum is 8. Among all the maximum, take the minimum. That minimum is becoming 4. So max mean value is becoming 4 and minimax value is also becoming 4. Max mean becoming 4, minimax value is becoming 4. So this 4 is coming with respect to second row and third column elements. Second row and third column elements. So this 4 is known as the saddle point. This 4 is also known as the value of the game. Since it is positive, that is a gain for the player A. So, and these 4 units, player B will pay to player A. And what is the optimal strategy? Optimal means, so A is using his second strategy, B is using his third strategy. Okay. Now you can see here, instead of say here in this problem, what is his A's intention? A tries to maximize his gain. B tries to minimize his loss. One is trying to maximize his gain, other is trying to minimize. When A is trying to maximize, B is trying to minimize his loss. Okay, so if I'm considering second row, fourth column, so the element is 5. Second row, fourth column is 5, and second row, third column is 4. So which is better? Say for player B, which is better, 4 or 5? 4 is better because he's minimizing loss. So A is trying to maximize his gain. When A is trying to maximize his gain, B is trying to minimize his loss. Okay. So the solution of the game based on the principle of securing the best of the worst for each player. If a player A plays strategy 1, then whatever the strategy B play, A will get at least 2. Okay. So similarly, if A plays strategy 2, when whatever B plays, he will get at least 4. If A plays strategy 3, then he will get at least 3, whatever B plays. So see, a very simple things we are discussing. So if the player A plays his first strategy, whatever B plays, A will get at least 2 units. Okay. So A is getting 8, 6, 2, 8. So if player A selects his first strategy, whatever B plays, so this A's gain will be at least 2 units, 2 or 6 or 8, at least 2 units. Similarly, if A plays second strategy, he will get at least 4 units. Okay. If A plays third strategy, he will get at least 3 units. Okay. So similarly, with respect to, so if B plays his first strategy, so B plays his first strategy, so what is happening? He is playing his first strategy, so he will lose How much? What is the maximum loss? 887. If he is playing his first strategy, so this whatever the whatever he is losing, that is the gain for A. So 87. So he can lose at most 8 units. Okay, at most 8 units. And second, similarly, if B plays second strategy, he may lose at most 9 units. And if it is using third strategy, he may lose at most 4 units. And similarly, if he is using the fourth strategy, he may lose at most 8 units. Okay, so in this manner we argue. So thus, maximize his minimum return, he should play strategy 2. Thus, maximize his minimum return. So maximize his minimum return, he should play strategy 2. Okay. Now, if B plays strategy 1, then whatever A plays, he will lose maximum 8 units. Similarly, second strategy, third strategy, fourth strategy, there are maximum of this respective column. Thus, to maximize this maximum loss, B should play third strategy. This 4 equal to maximum of row minima. This is also equal to minimum of column maxima. So maximum of row minima is equal to minimum of the column maxima, also equal to value of the game, and this value equal to 4. This 4 is called the saddle point. So this is happening due to we are using pure strategy, no probability distribution is involved. So that is the value of the game is giving the nothing but their saddle point, and the value of the game equal to nu equal to 4 units. Okay. So here another way also we can conclude. Okay. So this also can be concluded using the method of dominance. Now you can see here. So how to consider the method of dominance for this problem? So the first row, the elements are 8, 6, 2, 8. Second row, first row elements are 8, 6, 2, 8. Second row elements 8, 6, 8, 9, 8, 9, 4, 5. And third row elements 7, 5, 3, 5. So see, if you compare the A2 and A3, second row and third row, 8, 7, 9, 5, 4, 3, 5, 5. See, for the player A, the elements having bigger value is better. For the player B, elements having smaller value is better. Okay, so if you compare the second row and third row, 8, 7, 9, 5, 4, 3, 5, 5. So this second row, values are all greater than equal to third row. 8 greater than 7, 9 greater than 5, 4 greater than 3, 5 greater than or equal to 5. Okay, so what you can do here? We can simply eliminate third row. So second row is better. Third row certainly we can eliminate, because this third row having lesser value, we can eliminate third row. Third row we are eliminating 7, 5, 3, 5, and if you compare second row 8, 9, 4, 5, so we are eliminating from this matrix third row. Third row we are eliminating. As a result, this is our outcome. Only we have, so A has 2 rows. So A1, A2, and B has so 5 columns, B1, B2, B3, B4. Now see here, and the player B, as I told, for the player B, the columns having minimum value is better, because when A is trying to maximize his gain, B is trying to minimize his loss. A is trying to maximize his gain, B is trying to minimize his loss. So you can see here B1 88, B2 69, B3 24, B4 85. So if you compare, so now compare with B3 and B1, which is better? B3 and B1, which is better? The lesser value is better for player B. Which is better? Who can say? B1 and B3.
B3.
B3 is better. So we are dropping B1. Now compare B2 and B3. Which is better?
B3.
B3 is better. So B2 we drop, B1 is gone. Similarly, B4 and B3. 8524. Which is better?
B3 again.
B3 is better. And ultimately, what remain? So we have only two. So first row, only one element. A has 2 rows. B has 1 column. Now, so as I told earlier, the row which has higher value, that is better. So 2 and 4, which one A will select? First or second?
Second row.
Second row. So B has no option now. So it's only second. So now as a result, we are finding only one value, one element, that is A2, B3. A2, B3 is nothing but our saddle point, nothing but our value of the game. So two ways we have solved the problem using the max min and minimax rule and using the method of dominance. So, you know, some first time we have dropped A3, second times you have dropped 3 different column, B1, B2, B4, and ultimately we are finding only 2 rows and 1 column. As a result, we are taking decision. The 4 is the value of the game, and that is the saddle point, and optimal strategy is A2 and B3. A2 and B3. It cannot be A1, B3. It has to be A2, B3. Okay. In case, for example, in this problem, if instead of 2, 3, 2, 4, if it is -2, -4, for example, finally it is given -2, -4. -2, -4. What will happen? -2, -4.
A will choose -2.
That will be because A is trying to, so that will be -2 because A is trying to maximize. Okay, so this will be instead of 2, 4, it will be -2, -4 means -2. That optimal strategy will change. Yet it will be, so it cannot be -4 because this will be, A is trying to, A is selecting, so A will try to maximize his gain. So -2, -4. So since it is -2 is better, so A1, the strategy 1 is dominating strategy 2. So A2 will be -A2 will be -2 will be the value of the game. Okay, that's all. So here there is another small problem. So we like to check. So this is a payoff matrix. The payoff matrix is given. So player A and player B. The elements are 1. So second row elements, one of them is Q. Q is not known. Q you have to find out. So and then in the first row elements 1, Q 6. Second row elements P 5, 10. Third row elements 6, 2, 3. Okay. So what is the question? The payoff matrix, the P and Q are two unknown. Okay. So question is find P and Q, that will make the entry 2, 2 is a saddle point. So let us know what is the value of P and Q, so that 2, 2, 2, 2 means second row, second column. What is the second row, second column elements? This 5. So 5 will be saddle points. Find P and Q so that our 5, the second row, second element, second column elements is our saddle point. How to find? So we'll proceed in this manner. First row elements, so 1, Q, 6. We are interested to take the minimum. Minimum. So 1 and 6. 1 and 6 and Q. So we do not know what is the value of Q. So you see, if Q is less than, let us say, 6. So Q is less than 6. So, and minimum, as you observe, minimum there is 1, 6. So 6 we will not consider. We will consider maybe. So among 1 and Q, minimum value is minimum of 1 and Q. Is it all right? 1, Q, 6. What is the minimum? Because Q is not known to us. So minimum of 1 and Q is the minimum. Okay. For example, Q equal to 1, then minimum is 1. So Q equal to 2, minimum is 2. So suddenly 6 we are not, so higher value we are not considering. Okay. So here, say we are considering something like, say, 1, minimum is 1 among this row, 6 is there. So among 1 and Q, so you know, minimum will be either 1 or Q. This is the minimum. Second row, P and 5, 10. So we are talking about the minimum. So minimum will be minimum of P and 5. Minimum row elements will be minimum of P and 5. Okay. The third row, 6, 2, 3. What is the minimum? Minimum is 2. Among this we are interested to find the maximum. First row, minimum, then maximum. So maximum we'll find out among. Okay. So maximum depends on the, he's saying, if saddle point is 5, and what is the value of Q and P. Now let us know about the column maximum. First column elements are 1, P, 6. 1, P, 6. So among 1, P, 6, we are finding the maximum. Maximum will be maximum of P and 6. And second column, maximum of Q, 5, 2. That is Q and 5. That is maximum. So okay, the maximum is Q, 5. Among Q and 5, this is the maximum. And third column, 6, 10, 3, maximum is 10. So here we have got row minimum, column maximum. So since 2, 2 is the saddle point, 2, 2 is the saddle point is 5. Saddle point is 5. So what is happening to this? We are interested to take decision about P and Q. So this Q, as you observe here, P greater than equal to 5. If P greater than equal to 5, what will happen to this? P greater than equal to 5. Simply our judgment, P is greater than equal to 5. What is happening to this? So minimum of minimum is 5. So minimum is 5 means this 5 is matching here. So the Q is less than equal to 5. Q is less than equal to 5. We are talking maximum. So this is also match. Okay. So now this is possible only if P is greater than equal to 5 and Q is less than equal to 5. Greater than equal to 5. Now can you verify? Now let me take, so P equal to 10. If I'm taking P equal to 10, what will happen to this? P equal to 10. 5 suddenly fulfill P equal to 10. So P equal to 10 means, so here, so Q will take later on, let us say. So here both fulfilled So if together P greater than or equal to 5 and Q less than or equal to 5. Okay. If you consider P greater than or equal to 5 and Q greater less than or equal to 5 together, then this 2 will be your saddle point. Okay, together. Okay, that is the answer. So answer say this 2 second row, second column element is your saddle point, and that is the value of the game equal to 5 if this is fulfilled. Okay, this. Third problem. So specify the range for the values of the game in the following case, assuming that the payoff matrix is given in this manner. So here another problem. So the payoff matrix is given. A has 3 rows, B has 3 columns. Say the elements are given. First row element 3, 6, 1. Minimum is 1. Second row element 5, 2, 3. Minimum is 2. Third row element 4, 2, 4. Minimum is 2. Among these 3 elements, we are talking about the maximum. Maximum will be 2. Now, column maximum, first column, maximum is 5. Second column, maximum is 6. Third column, maximum is 4. Now, among all the maximum, we are talking about the minimum. Minimum is 4. See, this 4 say something about say minimum of column maximum, and these two say maximum of row minimum. In general, say maximum of row minima is less than or equal to minimum of column maxima in general. Okay, so same thing here. This 4, so this 2 is less than equal to less than 4. Okay, so we say that the game has no saddle point. Thus, the value of the game. So value of the game. So we are interested to know value of the game. Value of the game lies between 2 and 4. So 2 and not 2 and 3. This is 2 and 4. So 2 and 4. So this we are talking about a range. We are interested to find the a saddle point. This game has no saddle point. It's an unstable game. So now, if you are talking, so we can find the value of the game. The value of the game lies between 2 and 3. Okay, 2 and 4, not 3. This is 4 less than 2. Okay, less than 2. So less than 2. So in between you can find 4 and 2. Some number. Here both player must use random strategy so that A will maximize his minimum expected return and B will minimize his maximum expected loss. Another problem. So that the payoff matrix. So what we are calculating earlier. So that is, row wise you are taking the minimum, then you are maximizing. Okay. Then column wise you are finding the maximum, then you are minimizing. Okay. So this max min value of Aij is less than equal to minimus of Aij. If both are equal, then the game is stable. If it is strictly less, then the game is unstable. So this we like to prove. So solution. So let us say here we are talking about the Ri. Ri stands for the ith row minimum value. Ri, that is the ith row minimum value. So minima is over j, Aij, that is equal to Ri. And after finding the minimum value of all the rows, take the maximum value. The maximum value is becoming R. I'm repeating again. So Ri Ri is the ith rows minimum value. There are m number of rows and n number of columns. So if Ri is the minimum value, so there are m such row, we maximize the minimum value. So R equal to maximize Ri over I, that is giving R. R is the maximum value. Similarly, okay, so let Cj, that is the jth column maximum value. Okay, maximize over I, that is Aij, that is the individual column, that is maximum value, jth column maximum value is Cj. And what is C? C is the, take all the maximum value, then you minimize, that is our C. So we are finding here this Aij is less than equal to Cj and greater than equal to Ri. Okay. So with respect to this, Aij less than equal to Cj and greater than equal to Ri. Therefore, maximum of Ri is less than equal to Cj for all j. So therefore, maximum from Ri less than equal to minimum of Cj, or you can write R is less than equal to C. So same thing what we have established in a numerical example, we are observing same. R is less than equal to C. If R is equal to C, then the game is stable, otherwise it is a unstable game. Okay. Now we like to discuss something about the unstable game. If it is a unstable game, now how to solve such problem? Unstable game. Solution of, see, in the game theory, as I have already told, we use linear programming technique to solve the unstable game. Linear programming technique. For the stable game, it is very simple. So what you find here? For any game, so take the row-wise minimum, then find the maximum, then you take the column-wise maximum, then you find minimum, both are equal, then the game is stable. We'll find the value of the game and the optimal strategy. So value of game is unique, but the optimal strategy may be more, maybe 2 different points, maybe 3 different points, depends on the problem. So now we are interested to solve problem if the problem is unstable. Unstable means we are going to use some probability distribution. Solution of this in a pure strategy is no longer applicable. So you use mixed strategy. Mixed means some probability distribution will use. Whenever a game does not possess a saddle point, no saddle point, so the game theory advises each player to assign a probability distribution over his set of strategy. Mathematically speaking, let xi equal to probability that the player A will use his first strategy. Okay, A1 is x1, A2 is x2, A3 is x3. Similarly, AM is xm. So these are the probability. Since it is probability, x1, that is small x1 plus small x2 plus small x3 up to small xm, their sum equal to 1, and all x1, x2, xm, they are non-negative. Similarly, so if the player B using some probability distribution over his strategy, y1 is the probability of using his first strategy, y2 is the probability of using second strategy, and yn is the probability of using his last strategy. Y1 plus y2 up to yn, their sum equal to 1, and y1, y2 up to yn, they are all non-negative since they are probability. So we have introduced probability distribution for the strategy. In this context, Minimax criteria says the given player should select mixed strategy that minimizes the maximum expected loss to himself, or equivalently that maximizes the minimum expected gain to himself. So two-player, the player A is trying to maximize his gain and player B trying to minimize his loss. One is trying to maximize his gain, other is trying to minimize his loss. The first player, we can assume in this manner, first player is trying to maximize his minimum gain. Maximize his minimum gain. This gain, whatever, he is maximizing. Okay. And second player is trying to minimize his maximum loss. Second player is trying to minimize his maximum loss. Instead of saying so, we will say, since you are using probability distribution, we will say first player trying to maximize his minimum expected gain. Second player trying to minimize his maximum expected loss. One is trying to gain, other is trying to gain, another trying to say one is trying to gain, another trying to minimize the loss. Okay, in this manner. So here, should we continue or we'll stop here? Hello? This pure strategy, the mixed strategy, will continue next class. Okay, is all right? Hello?
Yes, sir. Yes.
So the mixed strategy, so where we are using the linear programming technique, so we will continue in the next class. And because after game theory, I will stop it because they have given the date, so maybe in the April sometime they will conduct the test. So you should have the time. Okay, so we'll stop here. Okay, thank you. So I have already uploaded the file for the transportation problem, assignment problem, and so the game theory also I will upload in the same MS Team. Please go through. In case you are not finding, please tell me. I will tell you where it is there. Okay, it is there in MS Team. Okay, yesterday I have uploaded. Is all right? Okay, thank you.
Thank you, sir.
Thank you, sir.